Hello, this is Jan. Today we will learn how to build a digital terrain model. We will call it also DTM for forestry scenery. Most likely it will also work for other scenery like city sceneries. They should be even more simple, but of course SimpleForest wants to model forests. So we will take first a preliminary ground point filter. It's called classify ground points. Here we have it. We will take the downscaled scenery. So I know already these parameters work, and mountain terrains you might have to increase this. I'm not sure, I don't have mountains access to mountain scans right now, and for low quality point clouds you need to decrease this parameter. I have observed it already. So, and you can also modify the grid resolution. This is from the ONF plugin, I didn't write it myself, so I don't know exactly the last parameter. So what we will do next is to put a ground point filter from SimpleForest, this plugin. You can choose here expert or non-expert. Non-expert will set you parameters. It will give you a little question and set parameters for you, but I'm not sure how good this works, but you can try out. So we will take the ground points. This is a result of this step as input, and then we will compute the normal. So first we downscale the point cloud to 4 centimeters. I want to be robust, that's why I downscale a lot, and I also take a large radio search for the normal computation. And then so after that I'm sorry, I just let's put it. I want to quickly show you the result. The computation already did start. So I messed up a little bit, excuse myself. So I said for each point the normal is computed, and we know that ground points are in the XY plane, so their normal should be showing towards the Z axis. So this filter simply computes the angle between the normal of a point and the Z axis, and this angle should not be larger than 25 degrees. So let's say for this stem here where the mouse is, all the normals look there where I show now with the mouse in the XY plane. And of course this is the Z axis, so we would have 90 degrees here, and those points, 90 is larger than 25, so those points will be removed. So but let's quickly check so the results. So that is what ONF plugin did give us. We can see here is some stems left, right? This is a stem, there is a stem, there is a stem, and this is what I imported in my ground filter, which is here the result. So this is now the ground points which are left over, and this is a noise, and we can see these stems have been removed efficiently, also all the smaller stems here. and here the really small stems. Everything has been removed. There is a dead tree, and it was removed. So it did work quite well. So in mountain terrain, you might need to modify this. You should always play around first with this parameter if you need to adjust. So the quality is already good, but we will put a statistical outlier filter to the ground points, of course. We want to improve a tiny bit more. And well, statistical outlier filter I always leave to the standard. If I want to do, sometimes I adjust this parameter, but I leave the standard deviation multiplier as a large factor, and I do a lot of iterations. I should have increased the number of points, the parameter, which was 2. It takes a while. So what I will do is I stop the recording, I will set the parameter to 9, and I will run the algorithm, and then yes, be right back. So I'm back. So what I did is I tested out the statistical outlier filter. It took 3 minutes. I didn't want to let you wait. It wasn't that good, so I tested also the Euclidean clustering filter, and I decided to not use filtering here at all. So we can see the Euclidean clustering filter. This is what remains, and it did remove quite a lot valid information out. We can also check the statistical outlier filter. This is a noise, and this is a ground, so here we lost quite a bit of information, and I don't want any of those filters. I decided that we are already good enough, so let's delete. We just have the 2 ground point filters, and now I want to use my SimpleForest filter. I just take the filtered points. So as ground cloud, and of course the group is selected, and then we want to select one more group as a root group. That is the top level group here. So it will put in the top level group the final DTM result, which makes it better to search for it later. So those 2 parameters I never change. It's just for computing the normals, and the cell size I'm also fine with 20 centimeter sized cells. So the first 3 parameters I never change. And so let's say each point has a normal computed. Of course, for ground points the normal is looking upwards, so towards the z-axis, and the angle between the z-axis and the normal doesn't have to be larger than 20. I just gave you the explanation of the ground point filter. So sorry, So just let's run. I will explain. So we have the complete ground points. It will fit one big plane into it. Then it will split all the ground points into 4, and it will put 4 planes into it, and each of the 4 planes has to be the angle between the child plane and the parent plane doesn't have to be larger than 20 centimeters, otherwise it breaks the iteration. If it's smaller than 20 degrees, I'm sorry, then it will continue until it reaches the cell size of 20 centimeters. So we can look at the result. DTM. I want to make it 3D. So I activate 3D mode and deactivate raster mode, and that looks quite nice. Let's blend in the ground points. It looks decent. And let's look from one time from below and one time from above. And if you can see all the ground points in both represent from above and below, then the DTM is good. And what can I tell you? Here in the corners we didn't have ground points, so the extrapolation is not really accurate. It's large raster cells, but we have 20 centimeter cells where we have points, so with decent amount of curvature like we would expect in a forest. This here is a forestry road, and that's why it looks so artificial, because it's an artificial structure in the DTM. And that is the tutorial. Have a nice day. So I just quickly want to give acknowledgements to Tobias Meissner and his lab from the University of Leipzig. You see here the acknowledgements. He provided me with the clouds. Thanks a lot, and goodbye. See you in the next tutorial.